Welcome to The Explainer. I am so glad you're hanging out with us today. We're diving into a highly practical, top-down guide on designing small slab culverts. And look, this isn't just a bunch of abstract theory. We're grounding this entire analysis on the meticulously compiled work of Deputy Executive Engineer V. Venkata Narayana, with a specific presentation crafted by SDO Keshav Raidas. If you've ever found yourself wondering exactly how civil engineers tackle repetitive infrastructure hurdles with such crazy precision, or how they guarantee safety across miles and miles of roads, you're in the right place. We're going to uncover the structural logic literally beneath the pavement.
I mean, just think about the sheer scale of highway networks for a second. Every single time a road hits a small stream, a drainage ditch, or a little geographic dip, boom, you need a structure. We're talking about thousands upon thousands of these small highway bridges dotting the landscape. So the big question is, how on earth do you standardize the design for all of these without having to reinvent the wheel every single time? How do you guarantee that structural integrity while managing huge public projects? Well, the secret is having a master blueprint. A reliable engineering cheat sheet that basically completely removes the guesswork for the folks out in the field.
All right, here's our roadmap for today's explainer. We're going to hit 1, the basics of slab culverts, 2, rules for span grouping, 3, key site calculations, 4, navigating the data tables, and finally 5, abutment component design. Let's get right to it.
Section 1. Basics of slab culverts. Establishing the parameters. So, when we talk about slab culverts today, we're specifically looking at structures with spans up to 6 meters. We aren't building massive suspension bridges here. These are the absolute crucial, everyday highway structures that actually keep our transportation networks moving. And the beauty of this is that the design doesn't rely on starting from scratch. They're governed by super precise, pre-calculated parameters pulled right from the IRC SP 13/2004 guidelines. And we're dealing with really specific material requirements, using robust concrete grades like VRCC M20 or M25 for the deck slab, and M15 for the foundation courses. It's a highly controlled, deeply regulated system. Section 2. Rules for span grouping, controlling the stream.
Now, there's a strict mathematical preference you've got to follow here. Whether you're designing a brand new culvert or widening an old one, the guidelines are super clear. Prefer odd numbers of spans. 1, 3, 5, 7, or 9 spans. That's what you want. On the flip side, you want to actively avoid even numbers like 2, 4, or 6. The source documents also point out an important geotechnical reality, which is that when you're dealing with these smaller structures, you might not always find a nice, hard, rocky foundation at shallow depths. But going back to that span rule for a second, why the strict bias against even numbers?
Well, it's exactly what this quote highlights. If you use an even number of spans, let's say 2 spans across a river, you're basically forced to build a pier right in the dead center of the crossing. The middle pier will be located right in the center of the stream and always obstructs the stream flow. By sticking to odd numbers like 3 or 5, you leave the deepest, fastest-moving part of that stream completely clear of concrete obstacles. It's just a brilliantly simple rule that prevents dangerous bottlenecks, stops debris jams, and minimizes long-term erosion.
Section 3. Key site calculations. Measuring the true height.
Okay. Take a look at this. This perfectly illustrates exactly where you take your field measurements. You've got the road top up high, the heavy structural abutments holding the middle, and right down at the bottom, the lowest bed level of the stream. And definitely notice that 0.8 meter arrow right in the middle. That is your absolute mandatory vertical clearance. Anchoring our math to the physical ground and the road top is step 1. You really have to understand these visual relationships before you start churning out the numbers needed to build the thing. Let's actually walk through how you calculate the overall structural height, which the guidelines call capital H. It's a progressive step-by-step formula. Step 1, grab the lowest bed level from your site survey. We'll call that lowercase h. Step 2, subtract the depth of your deck slab and your wearing coat, the top layer taking the traffic friction. And you have to be highly specific here. It's 75 millimeters if you're pouring a cement concrete wearing course, or 56 millimeters for a bituminous one. Step 3, add back that mandatory 0.8 meters for clearance we just saw. And finally, step 4, don't just use whatever raw decimal your calculator spits out. You actually have to round that number up to the nearest fixed H value, like 1.0, 1.5, or 2.0 meters.
Section 4. Navigating the data tables, the engineer's cheat sheet.
Now this right here is the holy grail for a field engineer. It's a simplified look at the massive reference tables provided in the pocketbook for highway engineers. Once you know your span length and you've calculated your standardized H value, you literally just read across the row. Let's say you have a 1.30 meter span. Boom. You instantly extract your bedblock breadth of 0.30 meters, your foundation width of 1.50 meters, and even the exact quantity of concrete required, 3.26 cubic meters. You don't have to stress over calculating bending moments on the fly. The agonizing engineering math has already been rigorously vetted and compiled into this cheat sheet, which makes things incredibly fast and undeniably safe.
And our final section, Section 5, Abutment Component Design, Building the Substructure. Even within these standardized guidelines, the rules do adapt a bit based on the size of your structure. Take the bedblock, for example. That's the crucial concrete cap on top of the abutment that the deck slab actually rests on. If your clear span is under 3.00 meters, the camber, which is that slight convex slope to drain water off the road, is strictly provided by varying the depth right within the bedblock itself. But if your span hits 3.00 meters or above, that rule completely changes. For those larger spans, you instead use a uniform 300mm thickness for the block.
Check out how clearly we can see the detailed tapering and thickness changes between the different substructure components here. We're looking at the main abutment cross-section right next to the return wall section. If you track the dimensions and that precise stepping at the base, you can see exactly how the geometry shifts. The main abutment has to carry the intense vertical load of the deck and constant highway traffic, right? Meanwhile, the return wall is mostly there just to hold back the earth of the road approach. Every single angle and thickness on these drawings is perfectly engineered to handle those vastly different forces safely. So, pulling all of this together, what's the ultimate takeaway here? By strictly sticking to these pre-calculated guidelines from the IRC and the tables we've explored today, engineers pull off three monumental things. First, they guarantee absolute structural consistency across the entire road network. Second, they ensure bulletproof safety because the complex math is already verified. And third, they save literally countless hours of redundant, risky design time out in the field.
Which brings us to the very end of our explainer. I really want to leave you with this final thought. Knowing that the math for spans up to 6 meters is already flawlessly solved, how will leveraging this proven engineering cheat sheet completely transform the speed and accuracy of your next infrastructure project? Think about the bottlenecks you can just eliminate overnight by simply trusting the tables. Thanks for geeking out on the structural details with me today. Keep learning, keep applying these principles, and I will catch you on the next one.